Very good morning, friends. We were dealing with various strategies for synthesis of peptides. We know that we have to protect the amino group, activate the carboxylic group of the amino acid, and react with the amino group of the second amino acid in which carboxy is protected. And the process is the deprotection followed by addition is repeated number of time until the desired peptide is achieved. As we have seen that there are solution phase synthesis and the solid phase synthesis. Solution phase synthesis has been used for smaller peptides and for larger scale manufacturing, whereas the solid phase synthesis has been utilized for synthesis of larger peptides. In solution phase synthesis, there are two strategies which are involved. One of the strategies is segment strategy, or it is called as convergent strategy. As the name indicates, the segments of peptides are synthesized separately and then they are joined through ligation. And this method of synthesis are very much useful for synthesis of larger peptides, which are difficult to produce in a sequential manner. For example, insulin synthesis. In insulin, it has A chain and B chain. A and B chain are synthesized as two separate segments, and both the segments are ligated and to obtain the insulin. This method is also used in solid phase peptide synthesis too. Another method is sequential strategy. It is also called as linear strategies. This includes the addition of one amino acid over the other and it goes on one after the other. Traditional method in solution phase synthesis, sequential strategies is used, and this is most widely used in solid phase synthesis. In both this solid phase and solution phase, both segment strategies and sequential strategies have been utilized. Today let us discuss the sequential strategy used for synthesis of oxytocin in the solution phase. This I am dealing it as a case study. Oxytocin is a nanopeptide. Oxytocin has the following amino acids: glycine amide linked with leucine, linked with proline, cysteine, asparagine, glutamine, isoleucine, tyrosine, and cysteine. The sulfur groups present in the cysteine are interlinked through disulfide bond. This synthesis has been achieved in this manner. This nanopeptide has a molecular weight of around 1007. First is the glycine. We take the glycine and activate its carboxy group as ethyl ester, and this glycyl ester is linked with leucine, in which N group is protected, and this, when it is treated, it gives leucyl glycine ester. The leucyl glycine ester obtained has been treated with hydrogen bromide and acetic acid, and the protection of leucine has been removed. The deprotected leucyl glycine is treated with N-protected proline, which reacts with this to give rise to prolyl leucyl glycine ester. And we know that glycine is present in this glycine amide. That's why this glycine ester is converted into amide by treating with ammonia and methanol, where the ester group is replaced by corresponding amine group to give glycinamide. The Z protection of proline is removed by treating with bromine and hydrogen bromide and acetic acid, followed by treatment with N protected and N and S protected cysteine, where we get the cystyl prolyl leucyl glycinamide. The protection group is removed by treating with hydrogen bromide and acetic acid, and the deprotected cysteine derivative is treated with asparagine, in which amino group is protected, and to give rise to the corresponding pentapeptide. The deprotection of the amino of asparagine is carried out by using hydrogen bromide and acetic acid, followed by treatment with N-protected glutamine to give rise to corresponding glutaminyl derivative. This is glutamine amino group is deprotected by using same reagent HBr and acetic acid and treat with N-protected isoleucine to give rise to corresponding isoleucinyl, glycinyl, asparaginyl, cystinyl, prolynyl, leucinyl, glycinamide. The deprotection is carried out by using the same reagent and then treated with N-protected tyrosine to give rise to a octapeptide, which is protectant group removed by using hydrogen bromide and acetic acid and treated with N-protected cysteine. Later on, this is treated with sodium in liquid ammonia and oxidized, where the sulfur in the cysteine are oxidized to form a disulfide bond. This is how the oxytocin has been prepared in the laboratory. Oxytocin was obtained from the animal sources before. Now it has been synthesized in the laboratory. In the next presentation, we will be dealing with the others peptide synthesis using convergent method. Till then, have a nice day. Thank you.